We mentioned that blood has two main components, the formed elements and the plasma. Let's look at the plasma to start with. Plasma is about 92% water. You're thinking, that's a lot of water. Well, yes, but that's also why hydration is so important. Because if you can't stay hydrated, the blood itself, this 92% plasma water, is going to have problems start decreasing. And as that amount of fluid in the blood decreases, the blood gets thicker and isn't functioning quite as well. But besides that, there's obviously 8% not accounted for. That 8% is primarily protein-based. Now, of that 8 remaining percent, about 54% is made up of albumin, the protein albumin. Now, this albumin protein is basically dealing with osmotic pressure. Nothing about osmosis, water pressure, it's helping to make sure that you have enough fluid in the actual blood itself. Now, most of these proteins are made by the liver, but just to give you a heads up, they're all important in their own right. So we have albumin, osmotic pressure. We have 38%, give or take, globulins. Now, globulins, there's an alpha, a beta, and a gamma globulin. The alpha and the beta, transporting iron, lipids, and fat-soluble vitamins. Now, that's important because all of these are necessary for certain things in your body. Iron is for hemoglobin, making your red blood cells. Lipids, fat, needed for almost every cell in your body. Can help with metabolism, can help with energy storage, or simply with the fat-soluble vitamins. Because you need these vitamins for functionality to be proper in all your cells. But now the gamma, so alpha and beta, that was that. Gamma is different. Gamma is dealing with antibodies. Antibodies are what will recognize other cells. You can have antibodies that recognize your own cells. You can have antibodies that recognize foreign cells, things that shouldn't be there. But antibodies will recognize certain markers called antigens on a cell's surface. There's a way of trying to recognize what is where, basically. So these globulins, alpha, beta, and gamma for that matter. And then we have, give or take, 7% fibrinogen. Now, fibrinogen, we'll deal with this later when we talk about clotting, like blood clotting, but just keep that in the back of your mind for now. Now, these percentages of the actual protein, I'm not so worried about. Just know that albumin is the main one, is the biggest one. The idea that, about 92%, so the majority is water, that's the important stuff. But I say exactly what was the percentage given for fibrinogen, you can always look that up, I'm not worried. So proteins, about 8%, give or take. Mostly, though, is water, about 92%. But there are other things in there. I said about that 8% because we still have these other things. Nitrogenous byproducts, think of urea. These are also found in the plasma. Now, they're not really taking up much space, or there's not really that much of them, because they're constantly being cleared out by the kidneys, being removed so they're not staying present. Nutrients, things like glucose, you have carbohydrates, amino acids. All those are being distributed throughout the plasma. So your blood picks them up, maybe in the intestines from what you ate, maybe from other cells where they had breakdown of cells and the components being recycled. But wherever these come from, they're then being redistributed to other places for recycling, or if they're just coming in from ingestion, you're taking them to the cells that need them. So as the cells need carbohydrates for energy, or they might need amino acids to build a structure, they'll pull these components out of the blood and use them at that time. Electrolytes have down here sodium, potassium, calcium, chloride, and bicarbonates. They're all constantly flowing in your plasma. Now, each one has its own purpose, but hopefully back from the nervous and the muscular chapters of the past, you know that sodium and potassium can deal with the resting membrane potential. You know they deal with the amount of water being retained. Bicarbonate here, for example, is going to deal with pH balance. Calcium, you need that for different nervous transmission, muscle transmission, and other components like blood clotting. Chloride helps out with balancing the pH, but also is balancing out the ion concentrations for that resting membrane potential. So there's a lot of different parts and pieces that the electrolytes can help with in your body. Respiratory gases. We already mentioned carbon dioxide and oxygen, so we kind of just go on past that. Hormones. We just covered a whole chapter of hormones last unit. So hormones are also being utilized here. They're all being carried and transported in the blood. All right, plasma's done. On to the formed elements. Now, the reason they're called formed elements, again, is because they're not all cells. In reality, the white blood cells are the only complete cells. You're saying, well, they're called red blood cells. It's a cell, but the red blood cells, the mature red blood cells, are not complete cells. Basically, the mature red blood cells don't have a nucleus. They pretty much don't have any organelles. Those were there during development when it was growing, but they're all removed before this mature, maximizing the amount of hemoglobin and maximizing the amount of oxygen that can be carried in the cell. And platelets, we've already said, they're just cell fragments. So really, white blood cells are the only complete cell in the formed elements. Now, these formed elements are usually only surviving for a couple of days in your bloodstream. Now, I'll say that usually because there are red blood cells that can go up to 3-4 months of time. But there's a lot of turnover as they get damaged, they get used up, they simply break down. So as I'm going through this, these blood cells are originating in the red bone marrow. So you're thinking, okay, red bone marrow, go back to the skeletal system, remember where that is. The red bone marrow is where most of these originate. Now, they originate there and they're sent in the blood. Once they're sent out to the blood, most do not divide. Think about the red blood cells. They have no nucleus. They can't divide. So you're having these really be produced, go out, function, die, produce more. It's a constant process. And it's not like they're producing all of them in one day. You produce some every single day because you have some dying off every single day. There's a constant process of the cells that are dying off, new cells replacing it, constantly turning over in your blood. So these growth factors, these hematopoietic growth factors, is things that are going to help the blood itself. So first off, we have erythropoietin. Now hopefully that rings a bell because erythropoietin, or EPO, we talked about in the endocrine chapter. Erythropoietin is produced by the kidneys to stimulate the growth of erythrocytes, or red blood cells. So that's erythropoietin. We then have thrombopoietin. Thrombopoietin is going to help promote megakaryocytes into platelets. Well, basically, these platelets, they're fragments of these megakaryocytes. So these large megakaryocytes are breaking off pieces. Those are the platelets. So we're basically using thrombopoietin to make the platelets. Cytokines. Now these cytokines are actually a grouping. We have colony-stimulating factors as one thing inside the cytokines. The interleukins is the other we'll talk about. But right now, these colony-stimulating factors are actually a grouping of themselves because there's more than one colony-stimulating factor. So all of these colony-stimulating factors, though, are helping to promote growth. We're looking at the growth of granulocytes and monocytes. Now, monocytes are one of the 5 types of white blood cells. We'll get to what those do in a little bit. The granulocytes is a grouping of 3 different white blood cells. Looking at your neutrophils, your basophils, and your eosinophils. We'll go through all of those later. But these granulocytes and monocytes are being produced from the colony-stimulating factors. Basically, that means 4 of the 5 of the white blood cells are being produced from these colony-stimulating factors. The other thing down here, these interleukins. Now, the interleukins themselves are dealing with differentiation and maturation of cells, immunity, inflammation. They're helping, for example, if you have an injury or a cut, they'll help stimulate the inflammation process occurring there. So help it to inflame to protect that environment. It'll help with the maturation of the different cells in your body as well. So it really is playing a multifaceted role here of dealing with immunity, dealing with inflammation, dealing with cell maturation. So these interleukins, again, there's more than one. There's interleukin 1, there's interleukin 2, with just a whole grouping. So yes, these are in the grouping of cytokines, but then you have a subgroupings. Each colony stimulating factor 1, colony stimulating factor 2, they're all inside of this grouping here. Hematopoiesis. Hematopoiesis is the process of cell formation. So say blood cell formation, sorry. So looking at how you make blood cells. They have these hematopoietic stem cells. Now these hematopoietic stem cells, also known as hemocytoblasts. But these hematopoietic stem cells will divide into all the rest of the formed elements. All 5 of the white blood cells, the red blood cell, the platelets, everything originates from these hematopoietic stem cells, or these hemocytoblasts. So this is where everything starts with. Now, this is found in the red bone marrow because that's where your cells are coming from for your blood. Remember, red bone marrow, axial skeleton, so think skull, vertebral column, looking at going into the shoulders, so think about the scapula, the very top or proximal end of the humerus. You look at the coxal bones, the very proximal end of the femur. So looking at all these parts that still have a red bone marrow when you're an adult. Because if you remember back, in a child, very young children, everything is red bone marrow. But as you age, a lot of that turns into yellow bone marrow. So we only have the red bone marrow primarily kept in the axial skeleton and the proximal portions of the appendicular. Now, all these new blood cells, they can't simply just jump in unless there's sinusoidal capillaries. Sinusoidal capillaries are capillaries that have larger openings. Openings specifically large enough to allow the cells to pass through. Most of your capillaries throughout your body, your arms, your torso, they don't have these. You don't want the full size cells leaking out typically. So, but in the red bone marrow, you want them to get into the blood supply. So you have these sinusoidal capillaries, larger openings allowing the cells to enter into the bloodstream. Now this one has a whole lot on here, so let's throw it up full screen. What you're seeing here is the growth chart for every one of the formed elements. So starting up top, you'll notice there is going to be this multipotent hematopoietic stem cell. Basically, that means that is the hemocytoblast. That's the cell that will differentiate into every other formed element. Now, as these cells differentiate, some of the cells will stay as a stem cell, which means they're going to come here and go back up. But the rest of them will then be divided into 2 pathways. You're either going to go down this lymphoid stem cell pathway or the myeloid stem cell pathway. We'll start with this lymphoid pathway first. The lymphoid pathway is all meant to make lymphocyte cells. So we go in from the stem cell to the lymphoblast cell. Hopefully remember the term blast is immature. It's still growing, it's still developing. From that lymphoblast, you can then go into either a small lymphocyte or a natural killer cell. Now, these natural killer cells we'll get to more in the immunity section because they're meant to basically destroy foreign particles. But in the blood chapter, we're focusing more on the actual lymphocyte, the one that is going to produce the T lymphocytes and the B lymphocytes. And we'll get to each one of these cells later as far as what they do, how to identify them. But for now, know that the one pathway is only for lymphocytes. Now the other pathway, the myeloid stem cell, you'll notice it can branch into 4 different cells. It can go into the monoblast. The monoblast is an immature cell that will eventually go into a monocyte, one of the 5 white blood cells. You then have this myoblast. The myoblast can differentiate into one of the other remaining 3 white blood cells: the basophil, the neutrophil, and the eosinophil. All right, that means those 3 pathways now have covered all 5 of the white blood cells. The remaining 2 pathways, you have your proerythroblast, which as developing will eventually get down into the erythrocyte. We'll go through this pathway in more detail as we talk more about the red blood cells. Our last one is the megakaryoblast, again developing. Goes in the megakaryocyte and eventually then gets down to the platelets. So these are the pathways, all of which are coming from this multipotent cell, the stem cell. So every one of these cells, all 5 of your white blood cells, your red blood cell, your platelets, every one of these things is coming from this hemocytoblast, this stem cell. So it's helping with originating for everything at this point. It all comes from the same cell that differentiates, branches apart, different pathways, but it all originates here. So a little bit about how the blood cells, as well as the formed elements in there, are all being developed and how they're being produced.